The universe is heading toward a final, unbreakable silence. This is not a fictional tale, but the scientifically predicted end of all things. The astronomer Carl Sagan once said that the cosmos is within us, and we are made of star stuff, a way for the universe to know itself. That connection makes the final fate of matter deeply personal. By the end of this journey, you will understand how everything, from the atoms in your body to the most distant galaxy, faces an ultimate end in absolute silence. We will uncover what happens after the last star dies and the final black hole evaporates into nothingness. How does it feel to know that every story the cosmos has ever told leads to the same quiet conclusion? Right now, we live in a cosmic springtime. Our galaxy is a whirlpool of light, a vast collection of hundreds of billions of stars, each a nuclear furnace forging elements in its heart. Enormous clouds of gas and dust collapse under their own gravity, igniting into new suns, while the titanic explosions of dying stars seed the cosmos with the very atoms that build worlds and life itself. This incredible dynamism is made possible by the universe's stored energy, a legacy of its explosive birth in the Big Bang, channeled through the unyielding laws of physics. Yet this brilliant display has a cost. The second law of thermodynamics acts as a one-way street for energy, a principle stating that the universe's usable energy is constantly spreading out and dissipating. Think of a hot cup of coffee left on a table. It does not get hotter on its own, it only cools down, its warmth dispersing irreversibly into the room. The entire cosmos is following this same path, moving from a state of concentrated, useful energy toward a final state of maximum disorder, known as entropy. This vibrant era of star birth and galactic drama is not the permanent state of the universe, but merely its most active and fleeting chapter. The magnificent dance of creation we see today is the very process that is slowly but surely exhausting the cosmic fuel tank, setting in motion the inevitable journey toward an unimaginable quiet. How does a cosmos so full of fire and fury begin to run down? The answer lies in the life and death of the very stars that define it. Cosmologists have mapped out several potential finales for the cosmic story, each one a dramatic conclusion written by the laws of physics. The ending we get depends on a few critical numbers, like the universe's overall density and the mysterious properties of the force we call dark energy. One possible finale is the Big Crunch. Imagine the entire expansion of the universe slamming into reverse. Every galaxy, every star, every particle would hurtle backward through time, collapsing together into an unfathomably hot and dense point, a mirror image of the Big Bang. It is a fiery, dramatic end. Another theoretical ending is even more violent, known as the Big Rip. In this scenario, the repulsive force of dark energy does not just push galaxies apart, it grows infinitely stronger over time. First, it would shred galaxy clusters, then individual galaxies. Stars would be torn from their orbits and planets ripped apart. In the final moments, the very fabric of space-time itself would tear, pulling atoms and even atomic nuclei into nothingness. Yet, based on our current observations of the accelerating universe, the most supported model is neither a crunch nor a rip. It is the heat death, also called the Big Freeze. This is not a dramatic explosion or a sudden collapse, but a slow, inexorable fade. In this scenario, the universe expands forever, its energy becoming so thinly spread and disordered that no new work can be done. This is the path of maximum entropy, the ultimate dissipation of all warmth and light. It is this quiet, chilling finale that leads us directly into the profound and absolute silence we are destined to explore. This mysterious fuel, dark energy, is the unseen hand guiding our cosmic destiny. Its discovery in the late 1990s sent shockwaves through the world of astronomy. By observing the light from incredibly distant stellar explosions called supernova, scientists made a startling realization. The universe's expansion is not slowing down as everyone had assumed. It is speeding up. Something was pushing space itself apart, and that something was given a name: dark energy. Think of the fabric of the cosmos as a vast, stretching rubber sheet. Gravity, the force we know and feel, acts like a hand pressing down on that sheet, trying to pull galaxies and matter together. Dark energy, in contrast, is like a constant pressure from within the rubber sheet itself, forcing it to stretch faster and faster. It is a form of repulsive gravity, an anti-gravity force woven into the very vacuum of space. As the universe grows, the matter within it thins out. The density of galaxies and stars drops. But here is the crucial detail: the density of dark energy may stay the same or even grow. This means its relative influence becomes overwhelmingly powerful over cosmic time. While gravity's pull weakens as distances increase, dark energy's push grows stronger. This relentless acceleration is what will ultimately isolate every structure in the cosmos. Galaxies will be pulled away from each other until they are lost beyond a horizon of darkness, setting the final, silent stage for the fate of all matter. 100 trillion years from now, the universe experiences its first great silence, the end of star birth. The cosmic gas stations have run dry. The vast, swirling clouds of hydrogen that once collapsed to form brilliant new suns have all been consumed, either forged into stars or cast out into the emptiness between galaxies. What remains are dark and silent islands, the great spiral arms of galaxies like our own Milky Way, once traced by the brilliant blue light of infant stars, will have faded into a featureless, aging glow. The last star has ignited, and no new one will ever follow. This is not an instantaneous event, but a slow, regional dimming that spreads across the cosmos until the final ember of stellar creation is extinguished. The remaining stars are on their own, burning through the last of their fuel with no hope of replacement. This moment marks a fundamental and irreversible shift. The universe is no longer a creative force building complexity and forging new elements. It becomes a system in managed decline, a clock that is only winding down. The vibrant cosmic spring has given way to a very long and very slow autumn. The brilliant main sequence stars that once defined the cosmos will all eventually exhaust their nuclear fuel. For the vast majority, including stars like our own Sun, this does not lead to a cataclysmic explosion. Instead, they will gently shed their outer layers into space, creating beautiful, glowing shells of gas called planetary nebulae. What remains is the star's exhausted core, exposed to the void. This is a white dwarf. Imagine crushing the entire mass of the Sun into an object the size of Earth. The matter inside is no longer ordinary. It is compressed into a state known as degenerate matter, a form so dense that a single teaspoonful would weigh as much as an elephant here on our planet. These cosmic cinders no longer generate new energy through fusion. They simply glow with the trapped heat of their former lives, fading slowly over trillions of years like dying embers in a vast, dark fireplace. For the most massive stars, the end is far more violent. Their final act is a supernova, a titanic explosion that briefly outshines an entire galaxy. In the aftermath, the core is crushed with such unimaginable force that protons and electrons are fused together, forming a neutron star. A neutron star packs more mass than our Sun into a sphere only about 12 miles across. Its density is so extreme that it is essentially a single atomic nucleus the size of a city. Some of these objects, known as pulsars, spin hundreds of times per second, beaming out radiation like a cosmic lighthouse. Yet even these incredible spins will slow, their beams will falter, and they too will begin a slow, dark cooling. This epoch, lasting for trillions upon trillions of years, will be populated by these faint, fading remnants. The universe will be filled with darkening white dwarfs, like a sky full of cooling diamonds, and silent neutron stars, the ultra-dense tombstones of dead suns. This is the era of degeneracy. It is not a sudden end, but a quiet, drawn-out prelude to an even deeper darkness. These objects represent a temporary, if immensely long, holding pattern for matter, a state of extreme compression enforced by the laws of quantum physics. But what happens when even these last glowing embers finally lose their heat? So what becomes of the worlds that once basked in the light of these dead stars? Consider our own Earth or any living world, billions of years after its sun has faded into a white dwarf. At first, such a planet might huddle close to the fading ember of its star, a dark rock holding onto the last vestiges of internal heat. But this warmth is fleeting. Without a sun, the planet's atmosphere will first freeze and then slowly be stripped away by the relentless pressure of starlight from other, distant stars. It will become an airless, frozen ball, its surface temperature plummeting toward absolute zero, the coldest temperature possible in the universe. Its geology will be stilled, its core frozen solid. It will be a silent tombstone orbiting a dying cinder. This isolation, however, is not guaranteed to last. Over these immense timescales, the stable clockwork of planetary orbits begins to break down. The galaxy, even in its old age, is not completely still. Occasionally, another star, itself a dark remnant, will pass uncomfortably close to a planetary system. When this happens, its gravity acts like a subtle but powerful nudge, disrupting the delicate gravitational dance that has held planets in their paths for eons. A planet could be flung outward, ejected from its system entirely to become a rogue planet, forever wandering the black emptiness between the stars. Alternatively, the perturbation could send it spiraling inward on a fatal trajectory, until it finally crashes into the surface of its dead parent star. But even without such a dramatic stellar encounter, no orbit is truly forever. The theory of general relativity tells us that any two massive bodies orbiting each other will very slowly lose energy by emitting ripples in the fabric of space-time itself. These are gravitational waves. For a planet orbiting a white dwarf, this process is incredibly weak, almost negligible. But given enough time, and we are talking about timescales so vast they dwarf the current age of the universe, even this tiny energy loss adds up. The planet's orbit will decay, an imperceptible tightening of its path that ends with it being torn apart by tidal forces, and its material forming a final, cold disk of debris around the white dwarf. So the ultimate fate of almost every planet is one of two paths, ejection or accretion. Most will be cast adrift into the interstellar void, dark nomads on an endless, frozen journey. The rest will be drawn back to their stellar origins, their substance accreting onto the surface of a white dwarf or falling into the immense gravity well of a neutron star. This is the final recycling of matter, not in the fiery forge of a living star, but in the absolute cold and darkness of a universe that has long since forgotten what light even was. And as these last structures, these planetary systems, finally dissolve, the stage is set for the decay of matter itself. What happens when even the atoms that make up these dead stars and frozen worlds are no longer stable? Even the grandest structures in the cosmos are not immune to this relentless expansion. The great galactic cities of stars, bound together by gravity for billions of years, will eventually face their own dissolution. This is not a sudden, violent event, but a slow and inexorable unraveling that plays out over timescales almost impossible to grasp. The first to go will be the galaxy clusters. These are the metropolises of the cosmos, vast collections of hundreds or even thousands of galaxies all orbiting a common center of gravity. For eons, this gravitational glue has held them together against the background expansion of the universe. But dark energy does not give up. As the acceleration continues, the space between the galaxies in a cluster stretches with increasing force. There will come a moment, trillions of years from now, when the outward push of expanding space finally overcomes the inward pull of gravity's handshake. The galaxies within a cluster will begin to drift apart, their mutual attraction no longer strong enough to hold them. Each galaxy will become a solitary island, set adrift in an ever-widening and ever-emptier sea of darkness. But the disintegration does not stop there. The individual galaxies themselves will begin to come undone. Within a galaxy like our Milky Way, stars orbit a common center, but they are not on perfectly stable tracks. Over trillions upon trillions of years, the rare but inevitable close encounters between stars act like a subtle gravitational lottery. When two stars pass near each other, their gravitational interaction can transfer energy, much like a slingshot. One star might be flung inward while the other is given a powerful kick outward. For that ejected star, this kick is enough to achieve escape velocity, freeing it from the gravitational hold of the galaxy entirely. This process, known as gravitational relaxation, happens extremely slowly, but given enough time, it becomes inevitable. One by one, stars will be evicted from their galactic homes. The beautiful, ordered spiral arms we see today, those great pinwheels of light, will slowly lose their definition. They will unravel and disperse, leaving behind a faint, diffuse halo of stars that drift further and further apart. This is the final end of galactic structure, the dissolution of the largest collections of matter ever bound by gravity. The universe, once organized into brilliant archipelagos of light, becomes a sparse and lonely scattering of isolated suns, each one a fading ember in an infinite, expanding blackness. The stability of the atom, the very bedrock of the material world, is not guaranteed forever. We have journeyed through the death of stars and the dissolution of galaxies, but now we confront an even more fundamental erasure, the potential unmaking of matter itself. At the heart of every atom in every frozen white dwarf and dark rogue planet is the proton. For all of recorded history and for billions of years into the future, these particles have been considered stable, the permanent anchors of atomic nuclei. Yet some of our most ambitious theories of physics, frameworks known as grand unified theories, suggest this permanence is an illusion. They predict that even the proton has a staggering but finite lifespan, a half-life so immense it is written as 10 to the 34 years, a number with more than 30 zeros. To grasp this scale, the current age of our universe is only about 10 to the 10 years, a mere blink in comparison. In a cosmos this old, the seemingly solid becomes ephemeral. Picture the nucleus of a simple hydrogen atom, a single proton. After this incomprehensible duration, that proton could spontaneously and randomly decay. It would not split apart but transform, breaking down into lighter, more fundamental particles like a positron, which is the antimatter counterpart of an electron, and neutral pions. These daughter particles would not last long themselves. The positron would quickly find an electron and annihilate in a final, tiny flash of gamma rays, while the pions would decay into pure radiation. This process would be slow and isolated at first. One atom in a frozen planetary core would vanish, then another in the heart of a dark white dwarf, each departure marked by a minuscule burst of energy. But over these epic timescales, the decay would become a universal tide. It would be a slow, quiet dissolution of the atomic universe. Every piece of normal matter, every last cinder of a star, and every wandering world would gradually evaporate into a faint, spreading mist of radiation and lightweight particles called leptons. The very concept of an object, of a solid thing, would lose all meaning. This is the final, profound end of the atomic era, an erasure so complete that it leaves behind a cosmos where the building blocks of planets and people no longer exist. Black holes become the final custodians of a darkening cosmos. In this new era, the universe is no longer a theater of light and fusion, but a domain of pure gravity. These are the only structures of any significant scale left, from remnants of massive stars a few times heavier than our Sun to the supermassive behemoths that once anchored entire galaxies, now wandering alone in the void. They are not active engines of destruction, but quiet, patient sinks of gravity, their event horizons marking the ultimate boundaries from which nothing, not even light, can return. Yet, in the profound quiet of this epoch, a subtle process begins to unfold, one that seals the fate of even these cosmic titans. The vacuum of space is not truly empty. According to quantum mechanics, it seethes with activity, with pairs of virtual particles and their antiparticles constantly flickering into and out of existence. Normally, these pairs annihilate each other almost instantly, but at the very edge of a black hole's event horizon, something extraordinary can happen. One particle of the pair might fall across the boundary while the other escapes into space. To an outside observer, it appears as if the black hole is emitting a faint glow of radiation. This is Hawking radiation. The black hole pays for this emission with its own mass, slowly and inexorably evaporating. For a stellar mass black hole, this process is agonizingly slow, taking longer than a googol years, a number so vast it is written as a 1 followed by 100 zeros. But in a universe with time to spare, it is a death sentence. The evaporation is not a steady drip. As a black hole loses mass, it shrinks, and its temperature rises, causing it to radiate more intensely. The final moments of any black hole's life would be a sudden, brilliant flash of high-energy radiation, a last whisper of its immense gravitational power. The largest supermassive black holes, having feasted on stars and gas for eons, would be the last to go, their final explosions punctuating a darkness that has already lasted for epochs beyond counting. What remains after the last black hole vanishes into a puff of radiation, leaving behind a universe with nothing left to consume and nothing left to give. Stephen Hawking's revolutionary insight showed us that even black holes are not eternal. They possess a faint, ghostly glow born from the quantum chaos at the very edge of reality. The vacuum of space, far from being empty, is a seething sea of virtual particles. These are pairs of particles and their antimatter twins that spontaneously blink into existence, borrowing energy from the universe for a fleeting moment before they meet and annihilate each other, paying back the energy debt. But at the precipice of a black hole's event horizon, this delicate dance is torn apart. One particle of the pair might fall inward, crossing the point of no return, while its partner escapes into the cosmos. To an outside observer, this escaping particle is real, and it carries away a tiny, almost imperceptible amount of the black hole's energy. This is Hawking radiation. It means black holes are not perfect traps. they are slowly, inexorably leaking. For a black hole born from a massive star, this evaporation is so agonizingly slow it defies comprehension. The process would take far longer than the current age of the universe, a timescale so vast it makes the lives of stars seem like a single heartbeat in comparison. But in a cosmos headed for an eternity of silence, even the longest timelines eventually run out. As a black hole loses mass through this quantum leak, a strange inversion occurs. The black hole shrinks, and as it gets smaller, its temperature actually rises. This causes it to radiate more intensely, which makes it shrink faster, creating a runaway process. The final moments of any black hole's existence would not be a quiet fizzle. After an almost endless period of slow decay, the last fraction of its mass would convert into an intense, brilliant flash of high-energy radiation and particles. It is the universe's final receipt, a last burst of light and heat confirming that even the most dominant gravitational structures are temporary. When the last supermassive black hole, the final relic of a forgotten galaxy, vanishes in such a flash, the black hole epoch is over. All that remains is a thin, cold sea of fundamental particles and photons spreading endlessly into the void. The last flash from the final black hole fades into an infinite and permanent blackness. This is the start of the dark era, the universe's final classical state. What remains is an expanse so vast and empty it defies human comprehension. The cosmos is now a thin, cold soup of the most fundamental ingredients. It is filled with photons, the particles of light, but these are not the brilliant rays of a sun. These are the last, deeply redshifted whispers of Hawking radiation and the faded afterglow of the Big Bang itself, now stretched to wavelengths larger than the cosmos once was. Mixed in are leptons, a sparse population of neutrinos, electrons, and their antimatter counterparts, positrons. These particles are the final, irreducible ashes of everything that ever was. There are no stars here, no planets, and no black holes. Every structure, every object, every single thing that could be called a thing is gone. The temperature of this entire universe is plummeting toward absolute zero, the point where all molecular motion ceases. In this profound cold, the remaining particles are so unimaginably far apart that they will almost never meet. A single electron might travel for timescales longer than the previous age of the universe without ever encountering another particle. This is a state of near maximum entropy. The energy is now perfectly, uniformly distributed. There are no hot spots or cold spots, no places of order or concentration. It is a universe where no work can ever be done again. No engine can run, no thought can form, no light can shine. It is the ultimate equilibrium, a silent, dark, and almost perfectly featureless expanse. This is not an end of destruction, but an end of possibility. The cosmos has not been ripped apart, it has simply and finally wound down. Yet, even in this absolute silence, a question remains. Could anything, even the vacuum of space itself, truly last forever? This final state of cold, dark equilibrium is what cosmologists call the heat death. It is the ultimate expression of a single, unbreakable law, the second law of thermodynamics, written across the entire cosmos. At its heart is the concept of entropy, which we can think of as a measure of the universe's disorder, or more precisely, its uselessness. A state of low entropy is one of high quality and concentrated energy, like a freshly poured cup of hot coffee sitting in a cooler room. The heat in that coffee is useful. It can power a small engine or simply warm your hands. But that state is temporary. The heat will inevitably flow from the coffee into the room, spreading out until both the coffee and the air around it reach the exact same lukewarm temperature. The energy is still there, but it is now useless, spread so thin that it can no longer do any work. This is a state of maximum entropy. The early universe was that hot cup of coffee. It began in an incredibly hot, dense, and orderly state, a cosmic singularity bursting with concentrated, useful energy. For billions of years, this energy has been powering the great cosmic engine, driving the birth of stars, the formation of galaxies, and the complex chemistry of life. But every star that burns, every planet that forms, every single process that occurs, is a step toward spending that initial inheritance. It is all part of the universe's one-way journey from a state of high-quality energy to a state of low-quality, dissipated energy. In the final dark era, the universe has reached its maximum entropy. It is that lukewarm room, but on a cosmic scale. All energy is uniformly distributed in a thin, cold sea of particles and radiation. There are no hot spots or cold spots, no places of higher or lower concentration. Without these differences, these energy gradients, nothing can ever happen again. No wind can blow, no thought can form, no light can shine. The cosmic clock has not stopped, it has simply run down, its spring completely unwound into an infinite and silent stillness. The temperature plunges toward an unattainable ideal, negative 273.15 degrees Celsius, a state known as absolute zero. This is the theoretical bedrock of cold, the point where the frantic dance of atoms and molecules grinds to a complete and utter halt. Yet, in this final dark era, the universe may never quite touch this perfect stillness. The relentless expansion of space itself acts like an infinite cosmic refrigerator, constantly stretching the sparse background radiation, the last whispers of light, into longer and longer, weaker and weaker wavelengths. The temperature drops ever closer to zero, but like a mathematical curve that approaches a line without ever crossing it, it only asymptotically nears that final, frozen state. This has a chillingly profound implication. For any process to occur, for any engine to run or any thought to form, there must be a difference in energy, a hot spot and a cold spot, a place for energy to flow from and to. In this final era, no such differences remain. The energy is perfectly, uniformly smeared across an infinite volume. It is a universe that is not just dark and empty, but one that has become fundamentally sterile, incapable of ever sparking a single dynamic process again. Even the residual heat from the death of the last black hole is stretched into a useless, undetectable murmur. This is the ultimate and unbreakable silence, a cosmos where the very conditions for change have been permanently erased. The numbers involved in this cosmic decay are so vast they defy our very ability to comprehend them. To truly grasp the scale of this story, we must stretch our minds across timelines that make the age of dinosaurs seem like a single heartbeat. Our universe is currently 13.8 billion years old, a span of time already difficult to hold in your mind. Yet this entire period, from the Big Bang to this very moment, is just the first fleeting instant in a story that spans trillions, quadrillions, and beyond. The end of star formation, that first great silence, arrives in the mere trillions of years. The grand spiral galaxies themselves take hundreds of trillions, even quadrillions of years to fully unravel and disperse their stars into the void. If protons do decay, they begin their slow dissolution on a scale of 10 to the 34 years, a number with over 30 zeros, and the most massive black holes, the last structures standing, will not fully evaporate for up to 10 to the 100 years. This number is so colossal it has its own name, a googol. A googol is larger than the number of atoms in the entire observable universe. These are not just long times, they are epochs so immense that the entire history of our cosmos, with all its stars and galaxies and life, is rendered into a single, brilliant flash of activity in an otherwise dark and silent eternity. This immense timeline underscores a humbling truth. The vibrant, dynamic universe we are privileged to witness today is not the norm. It is a fleeting, spectacular anomaly. We exist in a sliver of cosmic springtime, a brief window of light and complexity bookended by an unimaginably long winter of silence. Yet this silent fate rests upon a number so precisely fine-tuned it defies belief. The leading model of cosmic end times, the heat death, faces one of the deepest and most embarrassing puzzles in all of modern physics. It is called the cosmological constant problem. The cosmological constant is the name physicists give to the energy density of empty space, the very source of dark energy's repulsive push. Our most successful theory for the subatomic world, quantum field theory, allows us to calculate what this vacuum energy should be. The calculation is straightforward, and the answer it gives is monstrous. The vacuum of space should be brimming with so much innate, repulsive energy that the universe would have been torn apart in the first instant of its existence, before a single atom could ever form. The actual value we observe from the accelerating expansion of the cosmos is not just a little smaller than this prediction. It is about 120 orders of magnitude smaller. To grasp that number, imagine writing the number 1 followed by 120 zeros. That is the factor by which our theoretical expectation is wrong. It is the worst mismatch between theory and observation in the entire history of science. This is not a minor accounting error, it is a screaming paradox. Why is the energy of the vacuum so exquisitely tuned to be almost, but not perfectly, zero? If it were truly zero, the universe might eventually slow to a gentle halt, perhaps avoiding the ultimate isolation of the Big Freeze. If it were even slightly larger, as our theories insist it should be, cosmic structures would never have had a chance to coalesce, and we would not be here to ponder it. This incredible fine-tuning seems unnaturally perfect, as if a cosmic dial was set with impossible precision. This discrepancy is more than just a puzzle. It is a glaring sign that our understanding of the vacuum itself is fundamentally broken. It hints that a deeper theory, one that successfully unites gravity with quantum mechanics, such as string theory or loop quantum gravity, must exist. This future theory could reveal that the cosmological constant is not a constant at all, but a dynamic field that has decayed over time. Or it might show that our universe is just one bubble in a vast multiverse, a cosmic landscape where every possible value of the constant exists somewhere, and we simply find ourselves in one of the rare, habitable pockets where the number is just right for galaxies and life to emerge. The cosmological constant problem assures us that the final silence of the heat death is not the last word. It is the current best guess, but it rests on a foundation we know is incomplete. The ultimate fate of the cosmos may yet hold surprises, waiting to be uncovered in the elusive laws of quantum gravity. Yet the profound silence of the heat death is not necessarily the final verse in the cosmic story. Competing theories, born from the most ambitious frontiers of physics, offer a radically different vision, one of eternal return. In the Big Bounce scenario, the universe avoids the final fade by embracing a cyclical rhythm. Imagine the expansion of our cosmos eventually reversing, not into a definitive end, but into a great contraction. All matter and energy would collapse back toward a single, incredibly dense point. But instead of stopping there, the immense energies and pressures at that moment would trigger a rebound, a bounce that becomes a new Big Bang. In this model, the universe is like a cosmic lung, breathing in and out across eons, with each exhalation creating a new cosmos from the ashes of the previous one. The silent, dark era we have been exploring would simply be the quiet, transitional phase at the very peak of the universe's expansion, the moment of stillness before the long fall back toward rebirth. Another compelling idea comes from string theory in a model called the ekpyrotic universe. Here, our entire three-dimensional reality is just a membrane or brain floating in a higher dimensional space. Picture our cosmos as a single, immense page in a vast cosmic book. The Big Bang was not a moment of creation from nothing, but the result of our brain colliding with another parallel brain. This collision injected immense energy into our universe, setting off the expansion and heating we observe. Over trillions of years, the brains would drift apart, leading to the cooling and silence of a dark era. But eventually, drawn together again by some fundamental force, they would collide once more, igniting a new hot, dense beginning. In this cyclical view, every galaxy, every star, and every law of physics could be reborn in each new cycle, perhaps with subtle variations. These theories are not yet supported by the observational evidence that points toward perpetual expansion, but they stand as powerful reminders that our understanding of the cosmos is still in its infancy. They challenge the finality of silence, suggesting that even the most absolute end might just be a prelude to a new beginning, waiting in the dark. But even in this final, perfect equilibrium, the void might not be entirely dead. The rules of the quantum world tell us that empty space is not truly empty. It is a seething, foaming sea of potential, governed by a law known as the Heisenberg Uncertainty Principle. This fundamental rule states that we can never precisely know both the energy of a system and the exact time that energy exists. This allows for a bizarre loophole in the fabric of reality. Pairs of virtual particles, a particle and its antiparticle, can spontaneously blink into and out of existence, borrowing energy from the vacuum for a fleeting instant before annihilating each other and vanishing. In our current universe, these quantum fluctuations are tiny, momentary events. But in an eternally expanding cosmos, given a timescale that is literally infinite, even the most minuscule of probabilities becomes a certainty. The quiet of the dark era could be punctuated by rare, colossal quantum fluctuations. Think of it like a vast, silent ocean. For eons, its surface is perfectly calm and flat. But given enough time, the random motion of water molecules will, by pure chance, arrange themselves to create a single, perfect wave that rises up and then subsides. In the dead universe, a fluctuation could be so immense that it doesn't just create a pair of particles. It could spontaneously generate an entire galaxy, a solar system, or even a fully formed, conscious brain, complete with false memories of a life that never was. This bizarre concept is sometimes called a Boltzmann brain, named for the physicist who first grappled with the statistical nature of reality. The probability of such an event is so low it is effectively zero for any finite period. But against the backdrop of eternity, even events with a probability of 1 in a googol to the power of a googol are not just possible, they are inevitable. This introduces a deeply strange and unsettling philosophical puzzle. In the absolute silence of the cosmic end, isolated moments of subjective experience could flicker into being. A disembodied consciousness could appear from nothing, perceive a universe that does not exist for a single, fleeting moment, and then dissolve back into the silent vacuum from which it came. It is a haunting final thought that the universe's last whisper might not be one of light or heat, but a ghost of a thought, alone in the infinite and eternal dark. This profound, final silence forces a question that echoes far beyond the laws of physics. If every story, every memory, and every galaxy is destined to dissolve into an unremembered darkness, then what possible meaning can our brief existence hold? This cosmic endpoint brings us face to face with a central idea in existentialist philosophy, the notion that the universe itself is silent on the question of purpose. Meaning is not something we discover carved into the fabric of the cosmos. It is something we actively build, project, and cherish during our fleeting moment in the sun. The grand narratives of many religions and spiritual traditions which speak of eternal souls, cosmic rebirth, or a divine plan that unfolds across eternity are challenged by this stark scientific vision. The heat death offers no resurrection, no cycle of return, only an irreversible and absolute end. This realization can feel like a profound isolation, a confirmation that we are utterly alone in a universe that is ultimately indifferent. Yet this very indifference frames our existence with breathtaking clarity. Our significance cannot be rooted in eternity because eternity is silent. It must be rooted in the present, the fact that we are here at all, during this impossibly brief sliver of cosmic time when the universe is still ablaze with light and complexity, is a statistical miracle of staggering proportions. We are the universe become conscious, able to feel awe, to ask these very questions and to create meaning in the face of the void. The impending silence does not negate our lives, it illuminates them. Every act of love, every spark of curiosity, every work of art created is a defiant and beautiful assertion of meaning against a backdrop of ultimate oblivion. Our chapter in the cosmic story is infinitesimally short, but it is ours to write, and for a little while we get to fill the silence with our own light. Our own presence here is the ultimate clue to this cosmic timing. A natural and deeply puzzling question emerges from the silence. If the universe is destined to endure for a googol years or more in a dark and sterile state, why do we, as conscious observers, find ourselves alive in its first fleeting 14 billion years? The answer lies in a powerful idea known as the Anthropic Principle. In its simplest form, this principle states that the universe we are capable of observing must be compatible with our existence as observers. We could not possibly find ourselves in the dark era. Think about what is required for a complex, living being to exist. You need heavy elements like carbon, oxygen, and iron, which are forged only in the nuclear furnaces of stars and scattered by their explosive deaths. You need stable, long-lived planets orbiting those stars, providing a platform for chemistry and biology to unfold over billions of years. Most fundamentally, you need a universe with pockets of low entropy, where concentrated energy can flow from hot places to cold places, powering everything from solar systems to the neural networks in our brains. The silent, high-entropy future possesses none of these things. It is a perfectly uniform, cold, and dark equilibrium where no energy flows, no elements are formed, and no structures can exist. It is fundamentally incompatible with life or with any form of observation at all. Therefore, it is no surprise that we find the universe in its vibrant, low-entropy youth. Our very ability to look up at the stars and question the cosmos is conditional upon living in this specific, narrow window of time when such wonders are possible. We are not just random witnesses to cosmic history. We are privileged inhabitants of the one era brilliant and structured enough to produce us. We are the universe awakening to itself, not during its long night but at its glorious dawn. This paradox strikes at the very heart of our understanding of reality. Quantum mechanics, the rulebook for the subatomic world, has one inviolable law: information is never truly destroyed. If you were to burn a book, its information would seem lost in the smoke and ashes. But in principle, if you could track every particle of smoke and measure every photon of light emitted, you could theoretically reconstruct every word. The information is merely transformed, not erased. But what happens when the ultimate shredder, a black hole, is involved? When matter falls into a black hole, it carries with it a vast amount of information, the specific arrangement of atoms that made up a star, a planet, or a person. According to Einstein's general relativity, that information is locked away forever behind the event horizon, permanently removed from our universe. Then Stephen Hawking introduced his radiation. If a black hole evaporates completely, disappearing in a final flash, what happened to all that information it consumed? Does it simply vanish, violating the core principle of quantum mechanics? This is the black hole information paradox, a fundamental conflict between our two most powerful theories of nature. Most physicists today believe the information must be preserved, somehow encoded into the Hawking radiation itself, like a cosmic cipher imprinted on the escaping particles. It would be an incredibly complex and scrambled code, but in principle, the blueprint of everything that ever fell in would still exist, radiating back into the cosmos. So let us follow this information to the very end. In the dark era, long after the last black hole has evaporated, this information still exists. It is not gone. It is imprinted on the faint, cold photons and the sparse leptons that drift through the infinite void. Every particle carries a tiny, fragmented whisper of a cosmic history that can no longer be read. Imagine taking every book ever written, every song ever sung, and every memory ever held, and scattering their individual letters across an ocean the size of the universe. Then you cool that ocean to near absolute zero and stretch it forever. The letters are all still there, but they are so impossibly far apart, so randomized and diluted, that they can never be reassembled into a single coherent sentence. The information exists, but it is functionally meaningless. It has no capacity to inform, to instruct, or to tell a story. This is the ultimate nature of the cosmic silence. It is not an absence of data, but the total and irreversible loss of any narrative. The universe's final state is not an empty hard drive, but one filled with pure, random noise, the ultimate erasure of a meaningful past. Perhaps the most sobering consequence of this cosmic decay is the inevitable extinction of all complex structures, including life and intelligence itself. Every civilization, every mind, and every memory is a temporary phenomenon, a flicker of order in a universe sliding toward disorder. The immense timescales we have discussed offer no refuge. Long before the final black holes evaporate and the dark era begins, the last biological or technological beings will have vanished forever. Some speculative theories suggest a far future civilization might learn to survive the death of stars by engineering Dyson spheres around fading white dwarfs or even tapping the rotational energy of black holes. Yet this would be a desperate rearguard action against an unbeatable foe, the relentless increase of entropy. Each of these power sources is finite. A white dwarf cools, a black hole spins down, and the usable energy they provide steadily diminishes. The civilization would be forced into a state of perpetual retreat, its complexity slowly simplifying as the available energy flows weaken. There will come a point, long before the universe reaches maximum entropy, when the energy gradients become too shallow to power any form of computation or metabolism. Consciousness, the universe's most remarkable achievement, requires a constant flow of high-quality energy to process information and sustain its delicate order. When that flow stops, thought itself becomes impossible. This is the true finality of the silence. It is not merely the end of light and heat, but the absolute erasure of all subjective experience. Every story ever told, every feeling ever felt, and every question ever asked will reach its ultimate and unremembered conclusion, closing the cosmic narrative that began with the Big Bang. Our vision of this silent, dark eternity is a magnificent achievement of human reason, yet it is built on a foundation of profound uncertainty. The entire cosmic story we have just traced, from the death of the last star to the evaporation of the final black hole, rests on a critical assumption. We are extrapolating the physical laws we know today, general relativity and quantum mechanics, over spans of time so vast they dwarf all of human history. We are taking our best maps drawn from a tiny sliver of cosmic time and using them to navigate a journey of a googol years. The truth is, we have no experimental proof that the laws of physics remain immutable for such incomprehensible durations. It is entirely possible, even likely, that new physics waits in the darkness, a deeper layer of reality that could rewrite the entire final chapter. The enigmatic force of dark energy is the prime example. We have given it a name and measured its effect, but we do not know what it truly is. Is the cosmological constant truly constant, or could its strength change over eons? If it were to decay, the accelerating expansion could halt or even reverse, potentially opening a path to a cyclical universe. The vacuum of space itself, which we treat as a stable, empty stage, might be what physicists call metastable. Imagine our universe existing in a valley, but it is not the lowest possible valley. A deeper, more stable state of reality could exist. Through a random quantum fluctuation, our entire cosmos could suddenly tunnel into that lower state, a process called vacuum decay. This would not be a slow fade to black. A bubble of this new, fundamental reality would form somewhere in space and expand at the speed of light, rewriting the laws of physics as it goes. Every atom, every force, every structure it touched would be instantly and irrevocably transformed. For any observer, it would be an instantaneous end, followed by the birth of a new universe with entirely different rules. Even the constants of nature, like the strength of gravity or the mass of an electron, which we consider fixed and eternal, might not be so permanent. A complete theory of quantum gravity, the long-sought unification of the very large and the very small, could reveal that these constants are the result of how our particular universe cooled after the Big Bang. In another epoch or in another bubble of a multiverse, they could be different. This means our predicted heat death is the most logical conclusion based on our current, limited understanding. It is the best story we can tell, but it is a story that remains thrillingly unfinished. A testament to the fact that the ultimate fate of everything is still one of the greatest and most humbling frontiers of human curiosity. The confidence in this silent forecast comes not from a crystal ball, but from the ancient light that fills our telescopes today. We are cosmic archaeologists, sifting through the relics of the past to decode the future. The most profound of these relics is the cosmic microwave background, a faint afterglow that permeates all of space. This is the leftover heat from the Big Bang itself, cooled and stretched by 14 billion years of expansion into a whisper of microwaves. But this glow is not perfectly uniform. It contains a specific pattern of tiny temperature variations, a cosmic fingerprint imprinted when the universe was only 380,000 years old. By reading this fingerprint, scientists can determine the universe's precise recipe, its density, and the exact balance between dark matter, normal matter, and dark energy. This recipe is the initial condition for the entire cosmic story that follows. It tells us with remarkable certainty that there is not enough matter to pull the universe back together in a big crunch, and that dark energy's push is dominant, locking in the path toward the big freeze. The evidence is not just in this ancient light. When we look at distant galaxies, we see their light stretched to redder wavelengths, a phenomenon known as redshift. This is the direct signature of the expanding fabric of space, carrying these galaxies away from us. The most distant supernova appear dimmer than they should in a coasting universe, confirming that the expansion is not just continuing but accelerating. Every piece of data we gather from the present-day cosmos acts as a frame in a movie. We understand the physics governing the characters, the forces of gravity and dark energy. By pressing play, we can project the narrative forward with confidence. The silent end is not a philosophical speculation. It is the final scene that logically and inevitably unfolds from the opening credits we have already observed. This profound silence carries an emotional weight that can feel overwhelmingly heavy. It is a cosmic melancholy, the realization that every human triumph and tragedy, every work of art, and every act of love is destined to be erased as if it never was. This is the ultimate existential dread, the fear that nothing ultimately matters in a universe headed for oblivion. The scale of this erasure is absolute, promising a future where not a single memory of our world, our species, or our entire galaxy will remain. It is a quiet that feels like the deepest form of indifference, yet from within this chilling forecast, a strange and powerful counterpoint emerges. The very fact that we can contemplate this end, that we can trace the universe's story from its fiery birth to its cold demise, is itself a kind of miracle. Our consciousness is a flicker of light that can comprehend the surrounding darkness. This knowledge does not have to be a source of despair. Instead, it can be a profound liberation. If the cosmos offers no eternal meaning, then we are free, and in fact compelled, to create our own. The impending silence frames our present existence with a breathtaking intensity. It makes our brief moment of awareness, our sliver of cosmic time, infinitely precious. Every experience is heightened because it is transient. The warmth of the sun on your skin, the sound of laughter, the quiet satisfaction of learning something new, all of it is rendered more beautiful and more tragic because it is fleeting. This is not a reason to retreat from life, but a call to embrace it more fully. The universe may be silent in the end, but for now, it has given us a voice. Our story, however short, is a defiant spark in the vast dark, and that makes every moment of it immeasurably valuable. So what legacy can we possibly leave in a universe that forgets everything? On the physical timeline, the answer is a stark and absolute nothing. The pyramids will crumble to dust. Every digital record we create will be erased. The continents themselves will be rearranged and swallowed by the dying sun. Even the atoms that once formed our bodies and our world will eventually decay into a faint mist of radiation. If our legacy depends on leaving a permanent mark on the cosmos, then we are destined for total and utter failure. But this perspective mistakes the nature of a legacy. It confuses duration with significance. Think of a beautiful piece of music. Its value does not come from the fact that the sound waves persist forever in the air. The value is in the experience of the melody itself, in the emotion it evokes during the brief time it is played. Our human story is that melody. The act of looking up at the stars and unraveling their secrets, the act of creating a painting that captures a moment of beauty, the profound connection of love between two people. These are not valuable because they last. They are valuable because they happen at all. In a cosmos sliding toward silence, these moments of understanding, creativity, and compassion are brilliant, defiant sparks. They are the universe, through us, experiencing qualities that would otherwise never exist. We are the cosmos becoming aware of its own beauty and its own tragedy. This self-awareness is our true legacy. It is not etched in stone or broadcast into the void for an eternal audience. It is written in the quality of our brief, shared moment of consciousness. Our chapter may be infinitesimally short, but for a little while we get to fill the silence with meaning. This final transition from a universe of something to a state of near nothing is perhaps the most subtle and profound shift of all. We are left with a cosmos that is not truly empty, but one where existence has been stretched into meaninglessness. The void of the dark era still contains a vanishingly thin sea of fundamental particles, photons and leptons drifting eternally apart. Space-time itself continues to expand, its geometry forever stretching. Yet for any conceivable observer, this reality is indistinguishable from absolute nothingness. Nothing happens ever. The concept of an event, a change from one state to another, becomes obsolete. There are no hot or cold spots, no concentrations of energy, no differences that could ever initiate a process. It is a perfect and permanent uniformity, the vibrant distinction between something and nothing, a boundary that has defined reality since the Big Bang finally dissolves. This is not an ending that arrives with a crash or a final whisper. It is the asymptotic approach to a state of zero potential, where the very idea of something happening becomes a logical impossibility. The universe does not vanish, it simply becomes a silent, static canvas where no more stories can ever be painted. We have journeyed from a cosmos ablaze with light to one destined for an endless, frozen dark. The final fate of all matter is not a grand catastrophe, but a slow, inexorable descent into a silence so complete it transcends mere quiet. It is the state of maximum entropy, the universe's ultimate equilibrium, where every source of energy has been spent, every gradient leveled, and every story has reached its final, unreadable page. We have witnessed the death of the last star, the dissolution of galaxies, the decay of protons, and the evaporation of the final black holes. Each step was a move toward a simpler, colder, and more uniform state, a winding down of the cosmic clock. The poet T.S. Eliot once wrote, "This is the way the world ends, not with a bang but a whimper. Our universe's whimper is this absolute, unbreakable silence." Knowing this final chapter can feel like a weight, a cosmic melancholy that threatens to render our brief lives insignificant. Yet, this very knowledge holds a transformative power. It frames our present existence not with despair but with a breathtaking clarity. The universe, in its long and indifferent journey, has granted us a miraculous anomaly, a fleeting sliver of time filled with light, structure, and consciousness. We are the universe awakening to itself. We are the ones who can feel awe, ask questions, and create meaning. This ephemeral beauty is not diminished by the impending silence, it is defined by it. Our voice, our capacity to learn, to create, and to wonder, is the universe's most brilliant and temporary achievement. Let us use it fully, cherishing every moment of this cosmic springtime while it lasts. If this journey from light to silence has reshaped your view of our place in the cosmos, we would love to hear your reflections. Share your thoughts in the comments and subscribe to continue exploring the deepest mysteries of the universe together.